Thanks to Brilliant for supporting this video. If evolution is all about the survival and reproduction of the fittest individuals, then why are creatures sometimes nice to each other? In this video, we're going to build a simulation to start looking at the biology of altruism. Certain genes will code for certain types of behavior rules, and we'll see which kinds work from a gene's perspective. So what do our sims look like? Each day, blobs will go out to the forest to eat some fruit. Each tree has enough fruit to feed 2 blobs, but some of the trees have predators in them. If the blobs are unlucky enough to visit a tree with a predator, they'll get eaten. But if they don't get eaten, they'll head to one of the homes and reproduce, creating 1 or 2 new blobs in their place. And then the cycle repeats. There's no altruism yet, but let's make this a bit bigger and let it run for a while to see how it goes. Alright, so this little ecosystem is mostly stable. Now let's add the ability to be altruistic. When the blobs go to a tree with a predator in it, one of them will notice the predator and it'll have 2 options for how to react. The first option is to just run away, leaving the other blob to die. We'll call this the cowardly behavior. The second option will be to make a bunch of noise and warn the other blob, but in the process attract the predator's attention with a 50% chance of getting eaten afterward. Since these blobs are risking themselves to help others, we'll call this the altruistic behavior. The blob's behavior will be controlled by a gene, which has 2 versions or alleles. The cowardly allele will be yellow, and the altruism allele will be blue. Before we get to the simulation, it's worth saying that in real life, behavior is determined by a mind-numbingly complex interaction between many genes and a creature's environment over time, but this simple model is good enough to help us grasp some fundamental ideas. Okay, let's start with equal numbers of each allele and see what happens. This graph shows the frequency of each allele over time. At the beginning, half the alleles are the blue altruism kind, and stacked on top, half the alleles are the yellow cowardly kind. These values change over time, but they always add up to 1 or 100%. And speaking of the change, it looks like the altruism allele goes extinct after just a few generations. Maybe we made it a little bit too dangerous to be altruistic, so let's lower the death chance for being altruistic from 50% to 10% to see if the altruism allele can do well on easy mode. Okay, it took a bit longer, but the altruism allele still went extinct. Now you might think, hey, wait a minute, we only tried this once, maybe it'll do better some of the time? And yeah, that's a great point. So now let's repeat 30 versions of the same situation and see how that looks. Predict ahead of time what you think will happen. Do you think the altruism allele will always go extinct? Or maybe the first run was a fluke and the altruism allele will actually increase in frequency more often than not. Our brains like to pretend we knew things all along, so it's good learning and science practice to make a prediction before you see a result. So, what do you think? Okay, there's a lot going on in this graph. Each thin black line is one run, and the thick black line is the average. In some runs, the altruism allele lasted longer than others, but extinction seemed inevitable. Well, one did hang on for all 400 generations, but based on the other runs, it seems like it's pretty doomed in the long run. So why did this version of altruism fail? Well, this is a computer simulation, so we have a perfect record for everything that happened. There were 225,817 blobs saved by warning calls. 85,781 had the altruism allele, and the other 140,036 had the cowardly allele. And 24,151 of the altruistic blobs died after giving the warning. So overall, the altruistic allele saved a net total of 61,630 copies of the altruism allele, which is good. But since the total population size is limited by the predators, the total number saved isn't really what matters. More blobs being saved just results in more blobs getting eaten later on. What does matter, though, is the competition between alleles. A successful allele for altruism would need to find a way to help itself more than it helps its competitor. So how could we do that? Well, one way could be to let the altruism alleles see each other so they know who to help. But because DNA stays inside the blobs and doesn't have eyes, we need some detectable feature to go with the altruism. The classic example of this is a green beard, and that's a fun thing to put on the blob, so let's stick with that. So instead of the allele for altruism from before, we have an allele for green beard altruism. Now, when a blob with a green beard notices a predator, it'll only warn the other blob if that blob also has a green beard. So let's see whether this green beard strategy works in a simulation. And let's go back to the 50% chance of getting eaten after giving a warning. What do you think? Okay, that actually worked pretty well. The green beard allele drove the cowardly allele to extinction, and decisively so. But again, we should test it with many runs and with different settings. I ended up testing the 50% and a 90% chance of getting eaten for 30 runs each. In each case, what do you think will happen? Alright, at the 50% death chance, it seems like our first run wasn't a fluke. The green beard allele does indeed have a massive advantage. One of the runs got a pretty rough start, but it still ended up taking over before too long. At 90%, things are pretty noisy. Only 10% of the acts of altruism actually end up saving an extra blob. So the random fluctuations are pretty dominant. And even though the average shows an upward trend, the green beard allele does go extinct in several runs. After seeing these, I was curious to try again, but starting with only a 10% frequency for the green beard allele. Once again, what do you predict? Will the graphs look the same, just shifted down to start at 10%, or will something else look different? In the 50% case, there are a few interesting things going on. After a while, we see that the average goes completely flat, because in every simulation, one allele or the other has gone extinct. Of the 30 runs, 11 had the green beard allele take over completely, and the other 19 had it go extinct. Even though the green beard allele had an advantage and saw its frequency rise on average, it's still subject to the whims of luck when there are only a few copies, and once extinction happens, it's permanent. It's interesting to imagine what kinds of alleles might have appeared in the history of the Earth and could have done well, but just got unlucky. The second interesting thing is that it seems like the green beard allele's advantage depends on how many green beards there are. Each run starts out with mostly random wobbling, but when the density of green beards gets higher, the helping happens more often and they get more benefit. And in the 90% death chance case, things are just really chaotic, but we still do see an upward trend on average. Alright, so we have a simple version of green beard altruism working, but we should check to see how it does when things are just a bit more complex. Remember when I said earlier that in real life, behaviors are controlled by a complex interaction of many genes and the environment over time? Well, we're not going to be able to capture all of that complexity here, but we can at least notice that this one green beard allele is doing kind of a lot. It doesn't just code for the altruism toward green beards, which is complicated on its own, it also codes for the green beard itself. So as a small step toward a more realistic scenario, let's split those parts into two independent genes, each with two alleles. The first gene's alleles code for a green beard or no green beard, and the other gene's alleles code for altruism toward green beards or no altruism. And this means there will be 4 types of creatures. The blobs with no beard and no altruism will again be yellow and be called cowards. The blobs with no beard but altruism toward green beards will be blue, and they'll be called suckers. The blobs with a green beard but no altruism toward green beards will be red and called imposters. And finally, the blobs with green beards who are also altruistic toward green beards will be green and be called true beards. And it's worth clarifying that even though these blobs are now different colors for tracking purposes, the blobs themselves can't see the colors, they just see the beards. Alright, to set up the next sim, we'll start with equal numbers of all these types, and we'll go back to the 50% death chance. Also, this time, let's just skip ahead and run it 30 times and look at the averages. But before we do, try making one last prediction. Okay, in this case, showing all the lines from every run just gives us this Jackson Pollock painting, so let's get rid of those lines and just look at the averages. So what happened? Well, the altruism allele gets eliminated pretty quickly, whether it's paired with a green beard or not. The first to go are the suckers. They help, but they never get help. It's a tough world out there. The true beards do all right at the very beginning, just like before, but they end up going extinct in the end, because they end up sacrificing themselves for the imposters. And the more imposters there are, the more a true beard is in danger of sacrificing itself. And then there are the cowards that just kind of mind their own business. They don't do great, but once the altruism allele is gone, there's really no difference between the imposter and the coward. So their relative frequencies just bounce around randomly for the rest of the run. So it seems like green beard altruism breaks down with even a tiny bit of complexity. And as we'd expect from this, we've only found a few examples in nature. They aren't literal green beards, of course, but I've added some links to some papers in the description in case you want to learn more about them. Alright, those are all the systems we're going to look at in this video. To be honest, I actually find what we've seen so far to be a bit discouraging for making sense of altruism, especially in humans. We only found one type that worked at all, and it turned out to be really fragile in theory and rare in reality. But don't despair, we have a few more models to explore that are a bit more encouraging. And in the next video, we'll talk about kin selection, which follows Hamilton's rule. And while you wait for that video, why not level up your critical thinking skills with Brilliant? Brilliant has over 60 courses in math, science, and engineering, all with interactive components to help you learn deeply. And their courses are now available offline using their Android and iOS apps, so you can learn anywhere, anytime. I use Brilliant myself, and it's seriously really good. The first 200 people to sign up at brilliant.org/primer will get 20% off the annual premium subscription, and in the process, help support Primer. As always, thanks for watching.